Hi, I'm Dan Foley with Audio Precision. In this video, I'm going to present how you can use our new product, the APx500 Flex, to determine the health and well-being of your studio gear. But at this point, though, you might be asking, well, who is Audio Precision? We've been in business for well over 3 decades. We started in 1984 with the company founded by 4 engineers from Tektronix. Our first product, the System 1 audio analyzer, became an industry standard practically overnight. Our family of audio analyzers is used throughout the audio industry for development, test, and manufacturing testing of all the audio products that you use in your studio today. So why do a health check? Just look around your studio, you've got a very significant investment in hardware. That investment may even exceed over $1 million. And I'm sure that you or your colleagues in the business can recount situations where critical pieces of equipment went down before a very important session. What a health check enables you to do is to determine, what is the health of my equipment? Are there any issues I need to be aware of before they cause a session to stop dead in its tracks? Issues like distortion, issues that might come about when you do a wiring change, for example, installing new hardware in a rack. And speaking of hardware, at some point in time, you're going to be looking to add to the equipment that you have in your studio, whether you're looking to buy something used or buy brand new equipment. The APx500 Flex solution can also help you determine what's the condition of that equipment, especially if it's used, before you make the purchase. And if it's new equipment that you're looking at, you can confirm that the published specifications indeed do properly represent what that equipment can do for you. Let's take a look at the APx500 Flex Measurement software interface. The interface is divided into 5 main sections. The navigator is where you select the various measurements. The measurements available are dependent on which APx500 Flex license is purchased. In this video, I'm showing the measurements included in the base package, which includes level and gain, measuring the RMS level and gain at a single frequency such as 1 kHz. THD plus N, measuring the total harmonic distortion plus the noise with a single frequency. Stepped frequency sweep, measuring frequency response, gain, phase, and distortion at a series of discrete test tones. Loudspeaker production test. Even though the name of this test makes it seem it can only be used for testing speakers on a production line, we can use this to test the health of your studio monitors, microphones, and even electronic devices such as consoles and signal processors. In this video, we will use this measurement to characterize studio monitors as well as recording microphones. Real-time monitors enable you to view the output of what you are testing in real time. Available real-time measurement instruments include 2-channel oscilloscope, 2-channel FFT analyzer, monitors that show you the measured level, distortion plus noise, and the measured frequency. These tools provide you analysis capabilities that go well beyond what is available in a digital audio workstation. Signal path setup is where you choose which ASIO-compliant audio interface to use as your measurement hardware. Please note that all of the ASIO devices installed on your computer will show up in this drop-down menu. For the measurements we will perform, we will be using the Lynx Aurora 16-channel interface. Verify connections is where you are able to confirm that you have signal going into the device you are testing, as well as having signals coming out of the device back to your audio interface. There's a choice of test signals including sine-based signals, noise, both white and pink, as well as any wave file that matches the sample rate chosen in your audio interface. So let's make a quick measurement of our audio interface. We have the output plugged into the input of the interface and will generate a 1 kHz tone at 0 dBu. We can undock these live monitors to look at the measurements in greater detail. The oscilloscope can reveal any major distortion, such as clipping or asymmetry of the device's output. The FFT reveals what types of distortion are present, such as harmonics, intermodulation components, as well as the device's noise level. The right portion of the software interface is where you can view the measurement results. There are a variety of test signals you can use to check the health of your studio gear. The most common test signal used are sine waves. Here is an example of a 1 kHz tone being played at a level of 0 dBu going through an audio interface. The other types of test signals include various noise-based signals such as white noise, pink noise, or a special IEC noise signal that is weighted similar to that of long-term averaged music. There are frequency sweeps available as well. The sweep typically used for characterizing electronics is a stepped frequency sweep from 20 Hz to 20 kHz. Here's how that sweep sounds. The loudspeaker production test measurement uses a log chirp signal. Like the stepped frequency sweep, this signal starts at 20 Hz and ends at 20 kHz, but it's a completely continuous sine sweep, and it sounds like this. And as you can hear, it varies continuously. The benefits of using this signal is that you have a large number of excitation frequencies as opposed to the step frequency sweep. In the previous example, the step frequency sweep only had a total of 31 test tones. With the log chirp, there can be several thousand frequencies, which gives you much more detailed information about product performance. For this next measurement, we're going to check the time alignment of the left monitor versus the right monitor. The time alignment will ensure that the sound from both the left and right monitors arrive at the mix position at the same time. Proper time alignment is critical to ensure accurate monitoring. We are using a Shure SM81 microphone, as this microphone has a relatively flat response. We will first sweep the left speaker and then the right speaker, and we'll compare their time arrivals. Let's sweep the left speaker. Here's the frequency response. And here is the impulse response of the left monitor. Now I check append graph data, and we will run a second sweep of only the right monitor. Let's take a look at the results. The impulse responses are not on top of one another. This means the sound coming from the left monitor actually arrives at the mix position a little bit later than the right monitor. Based upon the difference in the peak levels of the impulse response, one speaker is a bit hotter than the other. When we look at the frequency response, we can see that it's about 2 decibels louder over a wide frequency range. Since these monitors have an input sensitivity adjustment, we will modify the input sensitivity and change the monitor position. We will now make a new set of measurements and see how well we've achieved our goals of time alignment and tonal balance. By adjusting the input sensitivity, the frequency response of left and right monitors is much more closely matched. This means that there is proper tonal balance. So what does the impulse response look like? The impulse responses are practically right on top of one another. This ensures that we now have proper time alignment with the left and right monitors. Let's use loudspeaker production test to measure a Shure SM81 microphone. Because this microphone is relatively flat, we need to use a measurement microphone which has a flatter response. This measurement microphone is available from Audio Precision. We will make this measurement in the control room because studio monitors can be difficult to move. The measurement microphone is positioned at the mix position. I will now run a sweep of the right studio monitor. I'll now remove the measurement microphone and position the Shure SM81 in its place. With the software's built-in post-processing capabilities, we can compare the speaker's response when measured using the AP measurement microphone in the Shure SM81. Since the measurement microphone has a flat response, we can do a simple ratio between the two frequency response curves. Here's the results showing the response of the SM81. When we compare this response to the manufacturer's frequency response, we see that there is a very close correlation, within a couple of decibels. This gives us a very good indication that this particular microphone is in proper working order. We will now use the loudspeaker production test measurement to characterize the frequency response of one of the studio monitors. Since we only want to ascertain the overall health of the monitor, we do not need to try and reproduce laboratory-type measurements that the manufacturer would perform in their product development lab. We just want to ensure that this monitor is in proper working order. Since we confirmed that the Shure SM81 has a flat frequency response to within plus or minus a couple of decibels, we will use this microphone as our measurement microphone. We are conducting this measurement in the studio's live room because the control room is too small and there are too many acoustic reflections. In the live room, the monitor is placed on a stool and above the floor by at least 4 feet. The measurement microphone is placed on axis in line with the tweeter and is positioned at a distance of 1 meter. We will now run the measurement and see the results. The frequency response and distortion show that this monitor is still within the original specifications. This ensures that the monitor is in good overall health. As you've seen in this video, APx500 Flex can be a valuable tool in ascertaining the overall health of key studio equipment, including studio monitors, recording microphones, consoles, and cabling and interconnects in your studio. If you want to get more information, please reach out to your local AP representative or distributor. You can get their information from www.ap.com. Thanks for watching.